Ho, 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 Merry Christmas to John, who's the only one who's going to watch this because everybody else is going to see it the first time live. And at the North Pole, yeah, all right. So anyway, we'll do a little calculus. So I did all the other talks, they can give you that, but definitely kept your great grandmother in your prayers, and my best friend growing up, who passed away. He would have been 51 today. So his name is Dave. And anybody else who needs prayers, the referee from last night, thank you to Hannah's dad for being there for him. That's pretty amazing. Yeah. So anyway, so we're going on section 4.2, or 4.1 and 4.2. Those are the two sections. You have all of my videos, so you really don't even need this, but I'm willing to do some additional stuff for you. But basically, I want 4.1 and 4.2 done when you come back. If you have questions on it, let me know. But get that stuff done so that I'm going to be kind of pushing you to get through chapter 4 anyway. And we do have a final exam to take. We only got like 2 weeks after you get back, right? Yep. So we need to get it done. Really, you should be probably doing through 4.3. But we talked about some antiderivative rules. So yesterday we had the antiderivative of x to the n power with respect to x is x to the n plus 1 divided by n plus 1 and plus c for a family derivative. So that was one of the theorems that we had. And this is true if n is not equal to -1. Well, if n equals -1, x to the minus 1 power is the derivative, antiderivative of 1 over x with respect to x. And by definition, this is going to be proven to be the natural log and the absolute value of x plus c. So these are the two things that we talked about yesterday. Really what we want, purple may show up better, it's a little darker. But anyway, if I have, we talked about the inverse of the exponential function. So the exponential function, f of x equals e to the x power. It explodes as x gets bigger, right? And it converges on the x-axis as x gets negative. E, remember, is approximately equal to what? 2.71828, et cetera, et cetera, et cetera. It's an irrational number that never ends, never repeats, like pi, right? So we like to give letter representations. Anyway, so that's e to the x. So of course, anything to the 0 power that's not 0 to the 0 power is what? 1. So the y-intercept of this is 1. But then the inverse of this, if you switch the y's and the x's, that's going to give you an inverse function. It's going to flip about the y equals x line, right? And if you solve to undo the exponential part, you take the natural log. So the natural log is going to look like this. So this is y equal the natural log of x is going to be this. And of course, the natural log of 0 is 1. Just like e to the 0 is 1. So the natural log of 1 is 0. What did I say? Natural log of 1 is 0. E to the 0 power is 1. They're inverse operations. And as you get close to 0, it's going to converge on the y-axis, right? It's going to get more and more negative there. So anyway, it looks like that, but that's supposed to be a mirror image. It doesn't really look like it, but it probably would have like your mind y equals x line a little bit better, right? So that's natural log of x. Of course, if I want natural log of the absolute value of x, what would the case be? I'm going to get rid of all this stuff here. I have a video on this, but what's the natural log of the absolute value of x? If I got the absolute value, then what happens? And the natural log of -1, if I plug that in, the absolute value of -1 is 1. So -1, 0 would be on the graph, right? And it would be a mirror image through the y-axis. So it would be a flip over symmetric with respect to the y-axis. So this is actually y equals natural log of the absolute value of x looks like that. And of course, it's not defined at 0. The natural log of 0 does not exist. Okay? So we have that, we got a couple things, then the other things that we talked about yesterday is the integral of the sum of functions is the sum of the integrals. Integral is another name for antiderivative. So if I say integral, I really mean antiderivative at this point. So we can just take the antiderivative of each part. So the antiderivative of f with respect to x plus the antiderivative of g with respect to x, and really that's f of x and g of x. I can also do that with a minus sign, right? So the antiderivative of the difference of functions is the difference of the antiderivatives of the individual functions, right? So we got that. One couple of theorems that we didn't have, so these are a couple of theorems. But if I have the antiderivative of a constant times a function, so k, let k be some numerical constant, basically what I can do is I can take that constant and I can pull it out front. I know what I should be doing. I should be using red and green for Christmas. What the heck am I thinking, boys and girls? I know at least 2 of you have been good this year too, so that's good. I don't think you want to know, Hannah. All right, but anyway, did I say your name? All right, but anyway, so I can bring that constant out front, and it's going to be the constant times the antiderivative of f of x with respect to x. So the antiderivative of a constant times a function, I can pull that constant out in front. Okay? So we can do that. Does that make sense? Any questions on that? So, by the way, we don't have antiderivative of a product. We don't have a product rule for this. We don't have a quotient rule for this. So you got to be careful on that. We had it for derivatives, but we don't have it to undo it. Remember, we're undoing a derivative to come up with an antiderivative. So anyway, so we got some different ones here. We could actually look at one here. How about I take the antiderivative? But do you want the sum of functions? Can we do one of those or not? Couple examples. All right. So examples: the antiderivative of x cubed plus 3x squared. By the way, it actually generalizes. So if I have like 3 or 4 or n different functions, the integral of the sum of the n different functions would be the sum of n sums of the individual functions. So if you have more than 2, it still applies. So you can add or subtract them. But anyway, let's just do this with respect to x, okay? So basically what I can do is say the integral of the sum, or the antiderivative of the sum of functions is the sum of the antiderivatives. So it's going to be the antiderivative of x cubed with respect to x plus the antiderivative of 3x squared with respect to x. Right? Now what could I do there? Could I use this rule here? Isn't this a constant times a function? So I can take that 3 and I can pull it out in front there, right? And so this is going to equal the antiderivative of x cubed with respect to x plus 3 times the antiderivative of x squared with respect to x. Of course, the antiderivative of x cubed, so we can do each part, and I'm going to give you a choice on how you do each part. But anyway, what's the antiderivative of x cubed? In other words, what did we say yesterday? The derivative of what is x cubed? That's an easier way to come up with it, but we can use our power rule for antiderivatives, and it's what? X to the 3 plus 1 over 3 plus 1, so it's x to the 4th over 4. Now, here's what I'm going to do. I'm going to put plus C1, because the reality is that one would be plus a constant, right, for a family? So anyway, that's this one. And then plus 3 times, okay, well, what I get here, the antiderivative of x squared would be what? X cubed over 3, and then plus C2, right? If I do that, so 3 times that antiderivative, of course, if I multiply that 3 through there, let's just do it in excruciating detail here. If I multiply that 3 through there, I got to multiply, I got to use the distributive law, right? And so what's this going to equal? This is going to equal x to the 4th over 4 plus C1, so that first part didn't change. And then plus The 3 cancels in the first term, and we just end up with x cubed, right? Remember, it's the plus 3 times that, so if this was a minus sign there, I'd be multiplying minus 3 times each part, right? So the sign always stays with the term that follows it. That's a nice algebra rule that for some reason no one was ever told. But anyway, but it's plus 3, so I'm taking plus 3 times each part. So if I take plus 3 times C2, what does that equal? What equals plus 3C2, but could I call it something else? Like C3 or PO? C3PO? No. Mouse don't move. Okay. Oh, hey. So, all right. But anyway, so I can just call it C3 because 3 times a constant is still a constant, right? But it is a different constant. You can't just call it C2. So if C2 was 5, that'd be 15, right? And it is different. But anyway, what can I do with the C1? Well, what's a constant plus a constant? It's a constant, right? So well, I can call it C4, but instead of C4, what would I call it? Was my hair messy? Both of them? Who said both of them? You're fired. What? Okay. Both hairs were messed up. Did you get that? Oh, yeah, I know calculus is easy, but your jokes are so hard, Professor Rowe. Oh my God, I'm on Christmas break, dude. Leave me alone. All right, anyway, I can just say plus C. How about instead of C4, I just call it C? Can we do that? Perfect. Okay. So anyway, now do you think I do it this way? No. No, of course I don't. What time do we get out? 1:15 or something?
1:14.
That's crap. Anyway, so I don't do it this way. Why don't I do it this way? I don't worry about the plus C for each part because I could have 100 parts. I don't want to put C1 through C100 if I got 100 different functions that I'm adding or subtracting together, right? So I just put the plus C on at the end. That's what I do, but that's me, Mr. Vegas. And yes, I deliver Christmas gifts there too. So, but instead of singing, you know, what does Santa sing? Ho, ho, ho. He sings ho, ho, ho. Here comes Santa Claus. Here comes Santa Claus. I sing, bright lights city, gonna send my soul, gonna send my soul. Anyway, to the little kiddies out there. That's a lot of money. That's a red. You know,
Yeah, but what about going to Vegas and being Elvis?
Being Elvis, yes, I have.
Have you ever done it?
Not yet.
Not yet.
Not yet.
When-
Anyway, but I have. I actually sung Elvis to my wife at her wedding, and it was on film, and I did good because my best friends didn't know I was doing it, and they couldn't tell if it was me or Elvis. It was actually a duet. I sang with Elvis into the mic, and the camera didn't get turned on. So I don't know how good I could have been. But anyways. Yeah, so anyway, by the way, how can I check this? So what do I do here? This is what I do. I say, well, that's x to the 4th over 4 plus a constant, right? But I wait. Plus 3 times, that's x cubed over 3, and then the 3's cancel, and then I'll put a plus c there, right? So anyway, that's just x cubed there. But how can I check my answer? I'm going to take the derivative back, right? So if I take the derivative back, so here's my answer. If I take my derivative so I can check it now, so I put check, I take the derivative with respect to x of all this stuff. So if I do that, the derivative of x to the 4th over 4 is 4x cubed over 4, which is x cubed, right? Because derivative constant, that's like 1/4 x to the 4th, right? Okay, so then those 4's cancel. I got x cubed there plus 3x squared. And then what's the derivative of constant? 0, right? And is that what I have in between the antiderivative and the dx? Yeah, so isn't that nice? Yeah, sugar and spice and everything nice, right? Huh? I don't know, what's that go? Is that a Christmas thing? Sugar and spice and everything nice?
No.
Yeah, whatever. It is now, I'm Santa Claus. Anyway. Here's a couple things. We got the antiderivative of sine is what? Well, so we got trig functions, right? There's 6 of them. You got a video for this if I run out of time. But anyway, that antiderivative sign, here's the derivative of what is sine. That's the easy way to do it. You got all 6 of them memorized, except for those of you that didn't get it on your test. The derivative of cosine is close. The derivative of cosine is what? Minus the sine, and I just have sine. So what do you think I need over here? I need the minus sign there. So the antiderivative of sine of x with respect to x is minus cosine of x, but then plus what? Plus c, and I like to make my c big because it stands for Christmas. That's what I say when I'm on the south side of the tracks in Carroll. Christmas. Wait, I live on the south side of the tracks in Carroll. Yeah, Carter thinks that's funny, Mr. Northsider. All right, but anyway, what's the antiderivative of cosine of x with respect to x? Well, the derivative of what is cosine? Sine. So it's just sine of x and then plus a Christmas. Christmas. What do you say on the north side? You live, which way do you live? North? West? Or what? Everybody see the sign light? Hey, I know that everybody's talking about the stars, but those are the planets are aligning you to take Calc 2, just saying. Planets are aligning right now, just like they did for the wise men of Jesus, and you're trying to be wise people, right? I'm just a wise ass, which was in the stable, so I could say that one. Oops. Anyway, so what's the other one? Well, what about this? There's some that I know, right? So if you take Calc 2, we do more of this stuff, like we figure out more of them, but the derivative of 1 is 16 squared. Huh? Tangent x. So it's the antiderivative of secant squared is tangent x. Now that's not just secant. If I said antiderivative of secant x with respect to x, there is an answer for that, but we don't have it yet. It's actually in the back, front and back flaps of your book. Have all kinds of different antiderivative formulas. But anyway, what else do we know? We know cosecant squared, right? The antiderivative of cosecant squared, well, the derivative of cotangent, the derivative of cotangent is minus cosecant squared, right? So we need a minus here. So that's minus cotangent x plus c. And then we have the other one, secant tangent, antiderivative of secant tangent, secant x tangent x. The derivative of 1 is secant x tangent x. Secant x. So the antiderivative of secant x tangent x with respect to x, secant x plus c. And then we have one more. We got the antiderivative of cosecant x cotangent x with respect to x. You need to know these just like you knew the other ones. The derivative of what is cosecant cotangent? Cosecant x, right? But it's minus cosecant cotangent. So I need the minus sign. So the antiderivative of cosecant cotangent x with respect to x is minus cosecant x plus c. And I meant to say cosecant x cotangent x. Okay, there we go. So those are some of the things. Hopefully you have enough to do 4.1 and 4.2. You look like you're ready to go. There's a couple of word problem stuff there too, but we do not have a product rule or a quotient rule for antiderivatives, so be very careful on that. We do have some other tools that we're going to use in this chapter and stuff too. The other thing that I didn't do in this section is like look at graphs. So just like we looked at graphs for the derivative, we can look at it the other way. So that's in there too. And then 4.2 is chain rule. So, which I was hoping to get to some of that today, but I didn't. So, anyway, you're gonna have to check out my videos because I'm out of time. I'm gonna go deliver gifts to the other good kid. One, yeah. So hopefully it's you.
Well, we're supposed to get out.